In this lesson, it's time to dive into the normal distribution. The normal distribution has a number of characteristic properties that we want to examine in this lesson, and then notice how we can use these properties to solve a number of problems. So normal distributions occur. You may have heard of the bell curve at university. I know I was an experienced student of the bell curve, where the median of a class, this is a class set of marks from 0 to 100, and this would be the number, this would be the frequency of students receiving a mark, and this would be from 0 to 100. And our mean was always around 66%. So if a particular class's results were too high or too low, they could be shifted left or right to fit so that the mean was at 67 or 66%. So a couple things. It's unimodal, meaning it only has one bump in it. It is symmetrical, so in a sense it kind of looks like a parabola, but it's different from a parabola in that its ends are asymptotic to the x-axis, which means they very closely approach but never ever touch the x-axis, whereas with a parabola it would continue past the x-axis. Some things that can affect the shape of this curve are the value of the mean and also the standard deviation. I'm going to talk about that in just a second. But one thing that is true about this distribution is that the area under the curve, no matter what its shift along the x-axis or its height based on standard deviation, is always going to be equal to 1. Or we can also talk about it in terms of percentages, which I'll address as well. So I've posted in the lesson plans a quick little link to Desmos that you can go to see exactly how the values of mu and standard deviation will in fact affect the shape of that curve. But again, I want you to remember that the area under that curve is always equal to 1. So some other neat things about this curve. We know that probability density is on the y-axis, but at the center, this axis of symmetry here, we have the mean. And what ends up happening because of the symmetry of this curve is that the mean and the median and the mode all end up being the same value in a normal distribution. Let's not forget that along the x-axis here we have our random variable, and it's a continuous variable, so there are all kinds of values it can have. What's neat about this curve is that if you go over the width of one standard deviation, both to the left and to the right of the mean, or if you end up going 2 standard deviations over, or ultimately 3 standard deviations over, you have a characteristic that is true for all normal distributions, and here is that characteristic. If I draw in lines for those particular values of being 1 standard deviation away in either direction, each one of these sections in here represents 34% of all of the data points. So collectively, they, if we look at them as an entire area, represent 68% of all data points, just within that particular range under the curve. And so actually what I'll do here is I'll write this in purple so that it corresponds with the idea of percents as well. Okay, so 68% is within plus or minus 1 standard deviation from the mean. If we go plus or minus 2 standard deviations from the mean, meaning that we extend out to here, and we look at the area of under that curve, it's going to be less than 1, it's going to be less than 100%, but we sure would expect it to be a lot closer to 100%, and it is. Each one of these is 13.5, and if you add all of these up, you end up with a range of 95% of all data points being within 2 standard deviations of the mean. And you can take this one step further. If you look at the area under the curve within 3 standard deviations of the mean, you can see that there's just this tiny little tail left that's not going to be included under the area of the curve, right? And it's going to go on and on and on and on until it almost touches. It's such a small, small fraction of the entire area of the curve. And the entirety of adding in these pieces as well to the others means that you are representing about 99.7% of all the data points for a continuous data set or for a normal distribution. So let's apply this to a real life scenario per se. Let's say that your mean for a particular data set, let's put a number in here, is 8.2. And let's assume that one standard deviation is worth 2.1. I'm going to write these off to the side here. So the mean is 8.2 and one standard deviation is worth 2.1. Okay? That would mean that 68% of the data, or this red area, is within this range. Can we figure out what this range is? Well, sure. I can add 2.1 up here to get to 10.3, and I could also subtract 2.1 here to get down to 6.1. So between the random variable values of 6.1 to 10.3, I would have 68% of the data. If I'm within 2 standard deviations, so I'll just add another 2.1 here or subtract it down here. Down here I'll end up with a minimum range value of 4, and up here I'll end up with a maximum range value of 12.4. All the data points for this random variable x that lie between a value of 4 and 12.4 would represent 95% of all of the data. And then finally, I could go to the third standard deviation, both above and below the mean. So up here I get to 14.5, and down here I would take away another 2.1 to get to 1.9. And so if I have data points with those particular values, 99.7% of all data points will fall within that range. Okay, so that's just really interesting. So how can we communicate all of this information in a really simple way to others? Well, really, the only things that we need to know are the value of the mean and the value of the standard deviation. So we have a short form notation we can do that with. We can write it this way. We can say that a random variable x varies in a normal distribution with the value of the mean and the value of, we use the variance instead of the standard deviation. So don't forget that variance is the square of standard deviation, which is this one here. So if I said to you, I'd like to communicate to you a normal distribution that has these values, could you draw it? And the answer is yes, you could. Okay, you could sketch it out because you would have 50 in the middle, and this is the variance, but the square of it, and that's important to note, means the standard deviation would be 4. So I could go 4 up to 54, 58, 62, and I could go down for 46, 42, 38, and I would know that 99.7% of all the data points would lie in a range between 38 and 62. Okay, let's continue on with some other examples. Now for this, I would like you to turn in your textbook to page 606 and 607. There's a table there that I normally photocopy and have off to the side that you can use when solving problems in a regular classroom setting. But because we're not in the regular classroom setting, you have a couple options. You could photocopy it if you want to, if you have a photocopier, or put a sticky note on those pages so that you can flip back and forth to it a lot, because we're going to be using it, and I'm going to show you how. Now, most of our questions related to the normal distribution have to do with finding the area under a curve. Now, finding the area under a curve is not like a uniform distribution where we've got a rectangle and we've got length times height, as we did in the previous lesson. So we need a couple of ways to find out probabilities of the random variable having certain values. And so we're going to look at a couple of methods. In this video, I'm going to look at method number 1, which is using Z-score tables from page 606 of your textbook. In the next video, we'll look at some other electronic ways as well. So method number 1 will be using Z-score tables. So it's important to note that there is a direct relationship between the value of a Z-score and the probability of an area under a curve. Okay, so at the top of the table, and this is the one that's from the back of your book, you'll notice that there are a couple things to note. We can relate a Z-score, which is shown here, and I'm going to show you how to use this table, and don't worry. There's a relationship between Z-score and probability if our normal distribution is standard. Standard means that its mean is at 0 and its standard deviation is a value of 1. Okay, so we have to have those criteria to use that. Okay, so let's take a look at how this works. Let's say that for our first example, you have random variable is normally distributed, so we can write it like this, with a mean of 0 and a variance of 1. Let's find out the probability for x being less than or equal to 1. Now before I do that, I kind of want to sketch out what this is going to look like. So again, I would have a mean of 0, and I could have 1, 2, or 3 standard deviations going above it and below it. So that would give me values of the square root of this, of course, is also equal to 1. That's our standard deviation. Because don't forget, this is variance. Okay? So 1, 2, and 3, and -1, -2, -3. So if we were to sketch out this curve, it would look something like this. Now I'm showing it touching, but we know it's asymptotic. I'm more concerned about this section here. Okay? And so if we want to know, first of all, what is the probability of this random variable x being less than or equal to 1, what it's really asking me for is, what is the area under the curve for 1 and under, or this here. Now, rough guessing, I mean, you know that this little section here is 34%, right? And you know that the section from 0 to the first standard deviation to the left is also 34%. And the next little section is 13.5%, and then this is a tiny little section. I didn't calculate it for you earlier on the slide, but you could. So, you know, I'm eyeballing this thinking the probability of x being less than or equal to 1 is going to be 68, another 10 is 78, number 3 be 81. We're looking at something just over 81, 82%. Okay, let's see how I can get that. Well, in order to do this, to find the area under this curve, we're going to learn how to use the table. We have to find out the z-score for this scenario. Now, this is from a while ago, but the z-score is equal to the value of x minus the mean divided by the standard deviation. Okay, so we talked about z-scores before in two-variable data. We really didn't use them. Here's where they're now going to come into play. So I look at my x value right here is 1, minus my mean, which is 0, divided by my standard deviation, which is 1. Well, 1 divided by 1 means 1. So what I'm going to do now is I'm going to convert this value, this z-score, of 1 into a probability, okay? And I'm going to do it using the table. So when I go to this table, I see that there are some negative z-score values starting at negative 2.9 and working their way up to 0. Okay, why 2.9? Well, the most number of standard deviations we're really concerned about is 3, and I'll talk about what this column is up above. And then we get to 0 and we do positives over here. So the left side has negative z-score values and the right side has positives. So my z-score was positive 1. So what I want to do is I want to scroll down this main column here until I get to 1. Now my value is actually 1.00. These tables can be used to 2 decimal places. So 1.0, if I were to stop here, this is the probability right there for 1.00. This top column shows you the second decimal place value. It goes from 0, 1, 2, 3, 4, 5, 7, 9, and then of course once you get to 10, you would have to slip down to the next 10th here. Okay, so 1.00 has a probability of 0.8413. Well, didn't we say earlier that it was going to be slightly above 81, 82% just based on the number of standard deviations it was that area includes? And sure enough, we're within reason. Okay, so let's try this again. This time, let's try and find the probability on this curve for when x is greater than or equal to 1. Okay, well again, it's important to note that these tables are for a given value, z value, and give us the area of the curve to the left of that z value. Here we're being asked for the area above 1. So what I'm really looking for this time is what's the area of this section under the curve. I'll show you where I mean. We're looking at it over here, greater than 1. So I can't get it directly from here, but what I could do is do 1 minus this section to give me this, and that's exactly what I'm going to do. So the probability when x is bigger than or equal to 1 is equal to 1 minus that orange area that I had before. Okay, this one up here. And I'm just going to color code so that you see where stuff comes from. I should have done that at the beginning. Okay, and I should have made this all orange too, but we'll keep it there. All right, so because I'm working not in percentages but in decimal form of probability, I'm going to do 1 minus the decimal, which is 0.8413, which means the probability or area under this curve is equal to 0.1587, or about 15.87%. Okay, so we can use these probabilities to look at sections that are exactly on standard deviations, but what about sections that are not exactly on standard deviations? So what if I said to you, what's the probability of having a value of x, or a data point, that's greater than 1.53? Okay, well, 1.53 would mean that I'm looking at something like this. I'm looking for the area under the curve this time of this section here. I'll just do this to color code it. Okay, so again, these z-score tables can't help me when I'm looking for areas that are greater than a certain value of x. So what I'm going to do here is I'm going to find the area of this section using the z-score table, and then I'll subtract it from the whole to get this piece. So let's begin by finding out what is the z-score in this scenario. The x value is 1.53. We subtract the mean, which is 0. we divide by the standard deviation, which is still 1. So we end up with a z-score of 1.53. Okay, so I want to convert that into a probability. Okay, so I'm going to do that using the z-score chart. So I'm in the positive regions of z, so I'm going to use the right side of this table. I'm going to scroll down till I get to 1.5. There it is. And then I'm going to go across until I get 1.53. And where the corners of my stickies meet, right here, is the probability for that really big area, which is 0.9370. Okay? So probability for x being less than or equal to 1.53 is 0.9370. So let's finish it. So therefore, the probability for when x is greater than or equal to 1.53 is equal to 1 minus when it's less than, which is 0.9370. So this comes out to being 0.063. If you want to communicate as percent, you can, but you don't have to. It would be 6.3%. And we would anticipate that that's a pretty small chunk of area under the entire curve, and so that seems reasonable to us. Now, we can also not just look at chunks at one end or the other. We can look at chunks in the middle too. So I'm going to leave that diagram up. And what if I said to you, what is the probability of an x value being between -1 and 1.5? So I'm going to sketch out where those bottom end and upper end thresholds are. So -1 would be about here, and 1.5 would be about here. So the question is asking me for the area under this section here. Now, this is not a one-step problem because our tables can't do that for us. But what I know is that this is 3 concrete sections that add up to 1. So if I want to find the middle piece, what I could do is I could think of finding the area under the curve here, and I could take away the area under the curve here, and that would leave me with that middle chunk, which I was trying to do sort of red and blue makes purple, but actually this should be the purple region right here if I want to make it truly color-coded, right? Anyway, doesn't matter. I want to find the area of this region here. I'll highlight it. Okay, so we're going to have to do probability from here under, subtract off the tail to get this middle piece here. I'm going to write that out in notation first, and then we'll have to do some pieces of work for that. So the probability of having an x value that's between -1 and 1.5 is going to be equal to the red zone I showed you, when x is less than or equal to 1.5, and we're going to subtract from it or chop off the purple section. Okay. So first step is we need to find some z-scores. We're going to have to find a z-score for the when this x value is -1. We're going to have to find a z-score for when it's 1.5 as well. Okay, so I'm going to write this under here. The z-score for when it's 1.5, and you'll be able to tell because you're going to put 1.5 in here. Okay, minus the mean, which is 0, over 1 standard deviation. These don't change for this particular curve. Gives us a z-score of 1.5. Okay, our z-score when x is negative 1, it's going to be negative 1 minus 0 over 1. And that comes out to negative 1. So we got to convert both of these z-scores now into probabilities. Okay, red and purple. So let's go to the table to do that. Because one of those values is positive, one's negative, I'm going to be using both sides of the table. Let's do the 1.5 first. So I'm going to scroll down first to 1.5. There it is. And it was 1.5 like that, but we know that the next decimal is a 0. So 1.50 gives me a probability of 0.9332. We used that in a previous example. Okay, so that's equal to 0.9332. Okay, now let's find the z-score the probability when the z-score was negative 1. So, going to the left side of the table, scrolling down, there's negative 1.0, and I want 1.00. I can do it to 2 decimal places. So my probability is 0.1587. Let's write that in. All right, so the probability of this middle chunk right here, the one that's shown in teal, is all of red minus purple. When we subtract them, we get a value of 0.7745. So there you have it. We can use those z-score tables to convert them into probabilities, and that way we can find the areas, which are the probabilities, under the curve for specific values or ranges of x. We'll look at some other ways to find these probabilities as well using some electronic software options.